Alright class, welcome back to another video on 7.5, which is using our sum and difference identities that we introduced in the last video. Okay, so this video, I should say, is going to be a lot of the same techniques, just a different way of delivering you the information. Alright, a different way of giving you the information, so you need to be able to kind of recognize what you need, pull it out of there, and then kind of complete the sum and difference identity. Okay, so if we read something like this, it's known that the sign of alpha, the sign ratio of alpha is 4/5 when alpha is between pi over 2 and pi. So let's look at that first. We know that the sign ratio has to be 4/5, and if we think about this, hopefully we understand this. We know that if alpha has to be between pi over 2 and pi, well then what quadrant do we have to be in? We have to be in quadrant 2. Alright, so that means that I'm going to draw my triangle in quadrant 2. I know that sine is opposite over hypotenuse, okay, so 5 will be the hypotenuse. Actually, let me just write that so we remember. I know that 4 must be my y value. And then in this situation, we can use, and actually I should draw this, so alpha's right there. In this situation, I know that if I have a 4 and a 5, well then this side must be 3. Alright, normally if we don't know the Pythagorean triple, we would have to use we would have to use the Pythagorean theorem to solve for that missing side. In this case, we should know that it's 3, 3, 4, 5, perfect. Big idea though, please make sure that you make that 3 negative because we're going in the negative x direction. Now, when we switch and we look at beta now, it says that beta has a sign ratio of -2 over root 5. Alright, so let's think about this now. Alright, I draw another set of axes. I know that beta must be in what quadrant if it has to be between pi and 3 pi over 2? Oh, that's quadrant 3. Alright, so we have our right angle. Here's my beta. I know that the sine, again, is opposite over hypotenuse. So I know that my hypotenuse will be square root 5, and I know that my opposite side must be -2. Now in this situation, I do not know the Pythagorean triple that's going to get me this missing side. So I'm going to solve for it. It's a leg, so maybe I'll call it A. Then my other leg is -2. Both of those together, when we take the sum of the squares, must equal c squared, or square root 5 squared. Alright? Well, let's see here. This will be a squared. -2 squared is just positive 4. Please remember that, right? A quantity squared will always be positive. And square root 5 squared is just 5. I can keep going here. A squared is equal to 1. A equals 1. When I put that 1 on the missing side, I remember that I'm going to the left, so I must make sure that I put a -1. Alright. So again, this is a different way of delivering you information. But now I have all 3 sides of multiple triangles, and I can figure out cosines, sines, tangents, etc., whatever we're going to need. So let's take a look at this. Well, A is nice and easy. The cosine of alpha just means I want the adjacent over the hypotenuse. Adjacent, -3 over hypotenuse, 5. Alright, so that's easy. I think B is going to be nice and easy as well. The cosine here of beta, adjacent over hypotenuse, is just -1 over root 5. If you've been rationalizing your denominators, then go ahead and write -root 5 over 5. Again, both of those answers in my book are perfectly okay. Now, for our sum and difference identities. We need to remember that when we're finding the cosine of alpha plus beta, we use a formula. We use cosine alpha, cosine beta, the sign changes, and then you go sine alpha, sine beta. Alright, so we use this formula, we plug in everything that we know. Let's see here. Cosine alpha, cosine beta, minus sine alpha, sine beta. Alright, let's plug in what we know. Well, we just found out in letter A that the cosine of alpha was negative 3/5. So I plug that in. Cosine beta, I found out in part B, was negative 1 over root 5. When I take a look, sine of alpha, well, I can either look at my picture or I can look at the original problem, and I can see that my sine of alpha is 4/5. And same thing with sine beta. I can look at the original, I can look at the picture. Either way, I should get negative 2 over root 5. Now we just clean this up. And to do so, we need to multiply our fractions. So a negative 3 times a negative 1 is a positive 3. And then I have 5 square root 5 in the denominator. I have a minus. 4 times negative 2 is negative 8, all over another 5 root 5. Okay, this is good. We already have common denominators. I can clean this up by switching to plus plus. So my final answer should just be 11, sorry, that's a plus, 11 over 5 root 5. Now again, I'm cool with this answer. If you used the rationalized value, if you used the negative root 5 over 5, it would have changed things around a little bit. This would have been negative root 5 over 5. This would have been negative 2 root 5 over 5. And you would have ended up getting what we would get now if we rationalize this denominator, which is 11 root 5 over 25. Alright, so there are both of our answers. This is the answer that we get when we do not rationalize. Alright, so that's kind of the one that I'm expecting from you. If you like to rationalize denominators, feel free to do so. Okay. Now, what's the difference between our sine formula and cosine formula? Cosine formula, you use the consistent ratios with the changed sign. With sine, we switch. Alright, with sine we switch. So, sine alpha, switch to cosine beta, same sign, cosine alpha, sine beta. Alright, so similar yet different. Similar yet different. Same values, different ordering. Let's make some parentheses so we don't get lost. The sine of alpha. The sine of alpha we said was 4/5, so I use 4/5. The cosine of beta we said was negative 1 over root 5, so I use it again. Let's see here. Cosine of alpha, negative 3 over 5. And lastly, sine of beta, negative 2 over root 5. Negative 2 over root 5. Okay. Once again, we start to clean up. Well, this is nice. I have negative 4 over 5 square root 5. This isn't bad. Positive, okay, so negative 3, so plus, negative 3 times negative 2 is positive 6, so 6 over 5 root 5. We have common denominators, we can clean this up to 2 over 5 root 5. Alright, so again, this is the answer that I would expect from people, because I'm not asking you guys to rationalize denominators. If you did rationalize your denominators from the get-go, I would expect something like this. Alright, so both answers perfectly acceptable. Okay, so this was a good kind of refresher on cosine sum and sine sum. Let's flip to the next page. Let's give you a new scenario, and let's see what's going on. Excuse me. Alright, so we have new angles, which means we need to draw new pictures. New pictures. Let's take a look here. Okay, so draw a diagram. 0 to pi over 2. That's nice. Okay, I know I'm in quadrant 1 here. Right angle, alpha angle. Sine is opposite over hypotenuse. So I know my hypotenuse is 3. I know my opposite side is root 3, which means I need to use the Pythagorean theorem and say a squared plus root 3 squared equals 3 squared, or a squared plus 3 equals 9. A squared equals 6. A equals square root 6. Alright, so now I have the three sides of that triangle. I can come up with any trig ratio I need for it. Alright. For beta, we have options here. I'm trying to think if it might be easier. For beta, what I want us to do, okay, so first thing, I know I have to be in quadrant what? If I'm going from negative pi over 2 to 0, beta has to be between negative pi over 2. Well, that's down here, and 0 is here. Okay, so I know I have to be in quadrant 4. That's good. Get this set up. I think what I'm going to do to make this easier, guys, is I'm going to unrationalize this again, right? 2 root 5 over 5, we know that that is the same as 2 over square root 5. Okay, so 2 over square root 5. That means now that because it's cosine of beta, which is adjacent over, what am I writing op for? Hypotenuse, excuse me. Well, that means that I now know that my adjacent side must be 2, my hypotenuse must be square root 5, and then I would probably want to use the Pythagorean theorem to get that missing side, the y length. So maybe we use 2 squared plus b squared equals square root 5 squared, or 4 plus b squared equals 5, or b squared equals 1. So of course we know that the y value is going to be 1, but because it's going down, please make sure to put a negative. Okay? Okay. Alright. I think that will be good because now, yeah, let's see how this goes. Let's see how this goes. So now when we move to the actual solving of these, or getting like the cosine of alpha minus beta, I need to remember my formulas. Again, cosine, we know that cosine is consistent in the ratios and it changes signs. So, cosine alpha, cosine beta, consistent in ratios, change signs, sine alpha, sine beta. Alright, let's see what goes on when we start plugging some stuff in. Cosine of alpha. Well, the cosine of alpha, we didn't actually write out anywhere, but we can get it from the picture, right? We know that the cosine is adjacent over hypotenuse, so square root 6 over 3. Cosine of beta, we actually were given, but remember we're going to use the unrationalized form. So we're going to use 2 over root 5. Alright, for sine of alpha, we're going to use, what do we have, root 3 over 3? Yes, root 3 over 3. And for sine beta, oh, sine beta is just y over r, or opposite over adjacent, so negative 1 over root 5. So when we start to clean this up, let's see here, we have a 2 square root 6 over 3 root 5. We also have a negative root 3 over 3 square root 5. And when I clean this up, 2 square root 6 minus square root 3 all over 3 square root 5. I'm okay with this answer right here, guys. If you had rationalized this denominator, or if you did not rationalize this denominator earlier, which is absolutely fine, right? Again, the whole idea of these ratios is that they're always going to be in proportion to one another. But if we go ahead and we rationalize this just for those people that did not unrationalize earlier, I would have to multiply top and bottom by square root 5, which means I should get 2 square root 30 minus square root 15 all over 15. Yes. Okay. Good. So again, this left answer is probably something more like what I would be looking for. And I think we are ready to check out the last problem. Yeah, alright, so tangent. We're only going to do one tangent. We remember probably that tangent is more difficult than the others just because of all of the fraction work we're going to have to do, okay? So hang in there. Keep doing what you know how to do. And we remember that the tangent formula says tan of alpha plus tan of beta all over 1 minus tan alpha times tan beta. Alright? Okay. So, when we look at the tangent of alpha, we want to use opposite over adjacent, right? Opposite over adjacent. Well, when we look at this in our picture, opposite over adjacent, or square root 3 over square root 6, well, this reduces, guys. This reduces to 1 over square root 2. Alright, so I think that would be better to use than square root 3 over square root 6. So I'm going to plug that in for my tan alphas. So, 1 over square root 2 plus, then I need to get my fraction bar, 1 minus 1 over square root 2. Alright, now we need tan beta. Well, tangent of beta is opposite over adjacent. Negative 1 half. Oh, negative 1 half. Great. We got this. Negative 1 half. Negative 1 half. Okay. Alright, so we have some fraction work to do here. We can't do anything with the numerator until we have a common denominator. What would we do here? And actually, you know what? Let's just go with it. Let's just do our normal work with common denominators. We know that we would have to multiply this by 2 and 2, this by square root 2 and square root 2, and I think that should work itself out nicely. So that'll be 2 over 2 square root 2, and then it would be minus square root 2, correct? Yes, minus square root 2 over 2 root 2. Now, let's take a look here. This will be 1 minus negative 1 over 2 square root 2. Sorry guys, a little bit off the page, okay? One more time, just because I realized I was off the page. All I did here was I made common denominators of the numerator, and in the bottom, so far, I've just multiplied this out to figure out what I'm going to do next. Alright, so I need some equal signs here. Alright, let's keep going. I want to make sure we understand that with the bottom, right, with the bottom, we need a common denominator again. Well, that means that I can rewrite this 1, and I'm just going to write it right on top of it. I think it would be better to write it as 2 square root 2 over 2 square root 2. Right? Because that's what the denominator is here. So let's take a look. I now have, and again in the numerator, common denominators means I can subtract across, and then I can do that subtraction again. So 2 square root 2 minus a negative means plus 1 over 2 square root 2. Okay, this is looking better. This is looking a lot better. All right, here. So now let's see here. Let's see. I know that when I have the same denominator in both of my fractions, what can I do? Cancel and cancel, which means I can rewrite this as 2 minus square root 2. And then, guys, what I'm going to do, just because I usually like to write my my radicals, I like to put the whole number first and then put the radical second. I'm just going to rearrange this. I'm going to change it to 1 plus 2 root 2. Okay? All right. Now the last thing, I think I want you guys to rationalize these. Okay? I want you to rationalize this one. So we're going to have to multiply by the conjugate. And if the denominator is 1 plus 2 root 2, well then that means I need to multiply by 1 minus 2 root 2. And if I do it to the top, or bottom, excuse me, I have to do it to the top as well. Alright? So let's take a look at what's going to happen there. Well, 2 times 1 is just 2. 2 times negative 2 root 2 is negative 4 square root 2. Then I come back, negative root 2 times positive 1 is a negative root 2. And the hardest one, I would say, negative root 2 times negative 2 root 2 is actually going to be a positive 4. Remember that a root 2 times a root 2 is just 2. So 2 times that 2 is 4, and remember that two negatives multiply to a positive. So plus 4. On the bottom, 1 times 1 is 1. My insides and outsides should cancel each other out. And then, let's see here, I have a little bit more work to do. 2 root 2 times 2 root 2, negative 2 root 2, means, well, these root 2's are going to multiply together to make a 2. So 2 times this 2 times this. Okay, so I have a negative 8. Again, 2 root 2 times 2 root 2 will be 4 times 2. There we go. Last thing I need to make sure to do, I need to try to clean this up as much as possible. So I have a 2 and a positive 4, which makes a 6. I have negative 5 square root 2, because these can combine. They're like terms, all over negative 7. And to finish this up, the last thing I should do, let me come down just for the one last step, or two last steps. I want to split this up, right? I know that both of these pieces in the numerator have a denominator of negative 7. So I'm going to write 6 over negative 7 minus 5 root 2 over negative 7. And when I clean that up, I should get negative 6 sevenths plus 5 root 2 over 7. All right? Okay. Wow, that was a lot of work. These tangent problems are definitely going to take some work and some practice, so make sure you keep working through them, and please make sure to ask me questions. All right? I hope that some of this is making sense. And I hope, honestly, I mean, as long as you guys are still doing okay with your ideas of cosines and sines and tangents, and again, using the triangles, then I don't think that this stuff should be too bad, because I know you're also good at algebra. All right? I hope you have a good day, and we'll work on this in class. Peace.